Hello everyone, my name is Benedict and today I will be speaking on behalf of High School Physicist. The goal of this channel is to talk about some topics in physics for an audience at a high school level or above. Hopefully this channel will inspire young generations to appreciate physics. To know more about this channel, please go and watch the channel introduction. Link is in the description. This video shows the audience an aspect of how physicists apply mathematical tricks to solve physics problems. Today I'm going to be talking about factoring mathematical quadratic expressions. This relates to the factorization of relativistic energy-momentum relation. The agenda for today is the introduction, the solution using algebra, the solution using matrix, factorizing relativistic energy-momentum relation, and finally the conclusions. To follow this video, you will need to have some mathematical knowledge about quadratic expressions, x squared minus y squared, matrix transposition, matrix multiplication, complex variables such as I, and complex conjugation. For example, the complex conjugate of 1 plus 2i is 1 minus 2i. In mathematics, we often encounter this quadratic expression. This is the difference of two quadratic numbers, and algebraically it can be factorized as x plus y times x minus y. Now, I want to substitute x squared with two numbers, x0 squared and x1 squared. How do you factorize this? There are two solutions. You can use the algebraic method or the matrix method. Afterwards, we're going to relate this matter to a real physics problem, that is to factor relativistic energy-momentum relation. Using algebra, the solution can be found really easily and quickly. First, we have to group x0 squared and x1 squared. Then, using this formula, we know that x is equal to the square root of x squared. So, using algebra, the result is the following. Now, we will discuss the solution using the matrix method. I think it's a bit more interesting than the algebraic method. Let's start with our original expression, x squared minus y squared. We will substitute x and y with a 2 by 1 column matrix. Please note that factor 1 over square root 2 is added for a reason. Now, we multiply x plus y by x minus y, using these two matrices. Please note that the x plus y matrix must be transposed. This is symbolized by the superscript t. Now we can simplify the equation. And then we transpose the first matrix. And finally, we get the correct answer. Now, can you explain the reason why I put the factor 1 over square root 2? We will still discuss the same problem as the last slide. But now we will introduce a 2 by 2 matrix. The 2 by 2 matrix is an identity matrix that doesn't change our original 2 by 1 column matrix. Then we again multiply x plus y by x minus y with these new matrices. Eventually, it'll give the identical answer as the previous slide. But why do we use a 2 by 2 matrix in this case? Let's find out. Now we apply our trick in the previous slide to solve our 3-variable quadratic expression. Substitute each variable with the same strategy. Now, multiply x0 plus x1 plus y by x0 plus x1 minus y. Please note that I selected addition against x0 and x1. And the result is not the same as our original expression. The sign is different on x1 squared, and also there is an extra unwanted term, 2x0 x1. Dear audience, please calculate this by yourselves for practice. Is it still possible to solve this problem using the matrix method? Is it still possible to solve this problem using the matrix method? Fortunately, the answer is yes. The matrices have saved us. We have freedom to play with our 2x2 matrices. Let us now change the matrix x1 with this 2x2 matrix, as shown in red. Let us recalculate x0 plus x1 plus y by x0 plus x1 minus y using these new matrices. Please be aware that this matrix has been transformed from this 3-matrix multiplication. This will be explained in the next slide. And the answer is correct. Please do this calculation again by yourselves for more practice. This solution is not actually unique. This means that you can find many other matrix combinations that satisfy this factorization. Now, let us tidy up our solution in the previous slide. We introduce 2x2 gamma matrices gamma 0 and gamma 1. I is a 2x2 identity matrix. Using these gamma matrices, our solution now looks more structured, neat, and consistent. Relativistic energy-momentum relation in physics is shown as in this equation, with E being energy, Px, Py, and Pz being the momentum component in xyz direction, m being the mass of particle, and finally c is the speed of light in a vacuum. More closely on this factor has the same form as our original problem, x0 squared minus x1 squared minus y squared, but with more terms. And so we will need bigger matrices, as shown on screen. Now, let's reformat this relation into a more compact notation that physicists usually use. Let us change the 4x4 matrices into gamma matrices, gamma 0, gamma 1, 2, and 3, then change the variables into P0, P1, P2, and P3. And the result is then. Since we used complex numbers, we have to use the complex conjugate for our first factor, denoted with superscript C. Also, the matrix in the first factor must be transposed, denoted with T. The factors can be compactly written as, with some conventions, the first gamma matrix must be multiplied by gamma 0. Complex conjugate must be applied and the matrix must be transposed. To note that there is a connection between our final result here and the Dirac equation. Dirac equation is an equation in physics that describes spin-half particles, such as electrons. In conclusion, we have factorized quadratic expressions via 2 different avenues: algebra and matrix. The solution using matrix method leads to an important application in physics, that is to factorize the relativistic energy-momentum relation, which subsequently derives Dirac equation. Dirac equation describes the spin-half particles in physics. I also have a YouTube channel where I post calligraphy videos. Feel free to go check it out. I also hope you enjoyed this video, as we enjoyed making this video too. Please consider subscribing and leaving a like to support this channel. Although the COVID-19 pandemic has receded, please stay safe. See you next time, and thanks for watching.